All right, let's start by adding a new class. We call it tree, and in this class, we're going to have a node class. So private class node. In the node class, we're going to have three fields. The first one is the value that we want to store, which is an integer. The second one is a reference to the left child. And the third one is the reference to the right child. Now, for simplicity, I'm going to create a constructor so we can quickly initialize a node with a value. So public node, we give it a value parameter, and here we set the value field. Pretty straightforward. Now that we have the node class, we can declare the root of our tree. So private node root. Now we're ready to implement the insert operation. So public void insert, which gets an integer value. Now here we have two scenarios. One scenario is where our tree is empty, so we simply set the root to a new node. In other scenario, we have to find the parent for this new node. Let's implement the easy scenario first. So if root equals null, we're going to set root to a new node with this value. And then we're going to return because we don't want the rest of this code to be executed. So let's test our implementation up to this point. Back to the main class, I'm going to create a tree class. Now, more accurately, here we have a binary search tree. So for a given node, the left child or the left subtree is always smaller, and the right child or the right subtree is always greater than the value of that node. Okay, so we have a tree. We initialize it like this and insert, let's say 7. Now I'm going to do a print line, just say done. Here I'm going to put a breakpoint and run this program using the debugger. There we are. So here's our tree object. In this tree, we have a root that is set to this node, and the value of this node is 7. Beautiful. Now to make things simpler, we're going to override the toString method in the node class so we can see the value straight away here without having to expand this field. Okay, so let's stop the debugger. Back to the node class. After the constructor, we override the toString method. So public string toString. And here we return a string like this, node equals plus value. We should also apply the override annotation. Now let's run the program using the debugger one more time so we see the impact of overriding the toString method. Take a look. So in this tree, we have a root node, and the value of this node is 7. Beautiful. Now let's implement the other scenario. So we have to iterate over the nodes in this tree until we find a parent for this new node. So we have to start from the root and go left or right depending on the value of those nodes. So I'm going to declare a variable called current and set it to the root. Now here we need a while loop. I'm going to make this an infinite while loop until we find a parent, because eventually we will find a parent. As soon as we find a parent, we will set this new node and break out of this while loop. So here we should compare the value that we want to insert with the value of the current node. If this value is less than current.value, that means we should go to the left subtree. So here we set current to current.left child. Otherwise, if the value is greater, we're going to set current to current.right child. Now let's visualize our tree. So we just added this root node with the value 7. Now let's say we want to add 4. So in the first iteration, we're going to set current to current.left child. Now in this example, we don't have a left child, so after this line, current is going to be null. And this is where things get a little bit tricky. Technically, we're looking for a parent for this new node. In this example, the parent is this node over here. So before we set the current variable, we should check to see if current.left child is null. If it is null, that means this node is the parent for the new node we want to insert. So I'm going to add braces around our first if statement. Here we need another if statement. If current.left child is null, That means we found a parent. So we should set current.leftChild to a new node with this value. And then we want to break out of this loop. Otherwise, we set current to the left child. So we go one level down. We need a similar algorithm in the else clause. So I'm going to add braces. Before we set the current variable, we check to see if the right child is null. If current.rightChild is null, that means we found a parent. So we set current.rightChild to a new node with this value, and then we break. Now, we have repeated this code, new node of value, a few times. I would prefer to create this new node at the beginning of this method. So let's declare it over here, new node of value. If root is null, we simply set root to this new node and return. And over here, when we find a parent, we simply set the left child to this node, and here we set the right child to this new node. That is better. Now let's test our implementation. So back to the main class. Let's insert another value like 4, and then 9, and then 1, 6, 8, and 10. Let's run the program and inspect our tree. So here's the root of our tree, the node with the value 7. On the left side, we have 4 because 4 is smaller than 7. On the right side, we have 9 because 9 is larger than 7. Now let's look at this subtree. So the value of this node is 4. On the left side, we have 1 because 1 is smaller than 4. On the right side, we have 6, obviously because 6 is larger than 4. Let's expand this left child. So here we have a leaf node because this node doesn't have any children. The same is true for this other node. Now let's collapse this node. On the right side of our root node, we have node with the value 9. The left child of this node is 8, and the right child is 10. So this is exactly the same binary tree that you saw in the previous video. We're going to work with this tree with these values throughout the section. So I suggest you to draw this tree on a piece of paper. So as we look at different algorithms, you can visualize what exactly happens under the hood. Next, we're going to implement the find method.